Welcome back to fsharpConf. And for our last long slot, we actually have two guests with us here who both happen to be interested in games. So we have Will, who's from the fsharp team, and Tanner, from which team are you?
CLI SDK.
Whoa. So many acronyms there. Who's starting?
I am going to start this one.
Okay, well, it's starting with a bit of Foom. And
Yes.
Halfway through, we will switch to Tanner, who will talk about hardware intrinsics in CoreCLR. So, Will, get started.
Okay, so the first thing I want to do right now is show this demo, and then I'll explain what is going on. So here I am in Visual Studio. I'm going to just hit run, and we should be able to see what this is. Hopefully the resolution is okay. Okay, so this may look familiar if you were playing games in the 90s. This is the first level of Doom. This is running on .NET Core, so it's running on the CoreCLR. And this has just been my side project for last couple years, just to try to figure out how to use F# in interesting ways. And so I decided to tackle this project. And I just found out a lot of interesting problems that you can solve in F# that's not always functional, but there are functional problems to solve, and I'll be able to share those to you. And so that's the kind of general gist of this. And so at a high level, I want to tell you how this is working, so at least you have some context of what I'm going to be talking about when I show you some code. So everything rendered here is in OpenGL. I have my own interop layer to be able to communicate with this. There's no bindings, and I'll show you how I handle this. And I am using the original shareware WAD file from the 90s, parsing it, loading it, and translating it to be able to let the GPU render this. That's the general high level of it. And it may not seem like much, but there's actually quite a bit of things going on here, and that's why it's taken me a couple of years to figure out how in the world I even do this from absolute scratch. So the only thing helping me here is F# and .NET at this point. And so that's the high-level context regarding this. So I want to go into a little bit of code to describe what is going on and show you where functional and non-functional or object programming helps when using F#. Okay, so the first thing I want to show you. So again, I talked about I'm using OpenGL, and OpenGL is not really a functional thing. Can you write a functional wrapper around it? Well, you could, but it's not going to give you a lot of benefit. You need to go much higher level to describe how rendering works. Here I'm still stuck in the low-level world. I need to be able to think in an imperative and object way to make things a little bit easier for me. So F# is multi-paradigm, so I'm going to show you some code where that paradigm actually helps me write this. So the first bit of code that you see here is really simple. It's just two types. One's a uniform, one's a vertex attribute. And what those mean in OpenGL, uniform is just an input, and a vertex attribute is also an input to a shader. And those are very inherently mutable things. You need to be able to set the inputs of a shader or change the inputs. So this is a mutable thing, and I have types representing this. And the reason why I have types representing this is because there's a lot of ceremonial things that you have to do in OpenGL in order to accomplish and get these inputs working and also not make a mistake. And that's the kind of idea behind creating these kinds of types. Now, how you express it, depends on what you want to do, but it's really as simple as this. I have a uniform vertex attribute. It has a value, has a name, and also has a location which is the location, an integer, an identifier that represents what is on the GPU. So that's at a high level. Now how this gets implemented and used is much more complex, and I don't want to go too far into it, but I'll try to describe it. So a uniform can be many different types, you know, an int, a float, vector, and so this all handles all the boilerplate and ceremonial work that you have to do in OpenGL. Like this to me is just nonsense. Like no one should ever have to write this. You should just write it once and just forget about it. And that's just basically how it's done. This is just a helper around it and uses a more object approach rather than a functional approach. And this is completely fine, and don't be afraid to go for using an object approach depending on the problem that you're doing. So that's how that's handled. Now I want to go into the interop, which I want to show you how I'm handling that and where functional actually programming came into play there. So the next bit of code I want to show you is the interop. And so how do I connect with C? Well, I built a tool that allows me to write inline C inside of F#, and you can do it technically in C# as well, but the C code is just as a string, so it seems kind of weird, but for me this actually worked pretty well. And this is just how I handle interop. I have this tool, just goes in, looks at this string, compiles it for whatever OS you're on. So this will work on OS X, this will work on Windows, and it'll compile to the right thing, and it'll give me an error if I do something bad or something that cannot communicate between the native and the .NET world. So that's what that does. Now you think, okay, this isn't really functional. Well, the tool that I wrote is a very functional problem, which I'm going to go into the next file. So I'll show you just a few examples because there's a lot here, but just kind of give you the general idea how I have to approach this is when a DLL has the C code, I need to be able to analyze it. I need to be able to find where that C code is at and make sure those types actually can work across in the unmanaged and native world. So I have functions that will take all that information, make sure that it's valid, and turn them into a very, very tiny CAST, which is basically nothing. It just kind of manages types. And so here are just some simple functions that just convert this stuff. And all of these problems are highly functional. There's no side effects or anything. There's no like hardcore native stuff that I'm doing here. I'm just taking some information from reflection and converting it over to an immutable type, which is the CAST. And what that looks like, this is the CAST. It's practically nothing. There's not much going on here. I'm not doing anything crazy with expressions. I'm just dealing with the types themselves. And so that's how I do this. I take all the things from reflection, turn it into a CAST, and once I do that, I then run it through a generator. So I have this really simple AST, and then it just goes through and calls these functions, and then outputs the C code. And this is all highly functional, and actually a very functional problem. I'm not having to worry about super fine-grained performance or anything like that. I'm just like, you know, here's AST, just build this thing for me. And so that's where the functional problem comes in when you try to compare it with all the shader work that you were seeing with the uniforms and vertex attributes. Very different problem. That one is an object style problem. This one is a functional style problem. They work well. Okay, so that's the gist of interop. And then now I want to get into, all right, so we have interop, we have shaders. Now how do we actually get the data that we need from one of these WAD files? So by the way, WAD stands for where's all the data. So on the parsing side, the first thing I do is, all right, Well, there's actually a spec out there online you can look at and see exactly how this stuff is structured. So this isn't me reverse engineering anything or even looking at original code. This is just looking at a spec that's been posted online, and I base everything on that spec. So the first thing I do is I create some types that represent the data that are inside these wads. And since this is just data, well, I can easily just create them as records, enums, even discriminated unions. So these are like very, very basic data and types that I need. Now, parsing data can be a very functional problem. Now, how does that work? Okay, so we look at this file that I have here called unpickle.fs. I really don't like the name. I guess pickle is really the right term, but I don't know. I just went along with it. I'll probably change it, but it doesn't really matter. So here, I'll show you a couple of things. For example, this right here. This is actually very functional. Here you don't see me reading anything from a stream. You don't see me calling anything that changes state anywhere. Instead, what you're seeing in this case is me just taking a couple of expressions and then composing them together that represents me reading a type, in this case, a side def. This is another functional problem, and basically another way to do functional programming, unlike what I was doing in the interop code. Because here I'm doing something a little bit more complicated, but I represent these expressions to do computation that can compose to each other. Now, that can give you some really powerful ways to express things without, having to worry about like, I have to do stream read byte, stream read int. You don't worry about that stuff. Instead, you just express things in these terms like, all right, I need 7 int 16, so I want to pipe 7 things. I want to int 16, int 16, int 16, and so on and so on. Then I get a function back with those values. And then I return a type based on those values. There's no notion of what stream is, or even if I'm using a stream on an array, it doesn't matter. You don't see that. All you care about is what you want to express. And that is another thing with F# that it allows you to do in can be a very sophisticated way. Now, sometimes you got to do the bad thing. Now, the way you express these things, you may hit a problem where it's really hard to express in these terms. And you know what? That is okay, because I'll show you an example. So here, this part, I actually do read from the stream directly because my combinators are not expressive enough to solve this kind of problem. I haven't thought about it enough to be able to do it effectively. So here I do the bad thing. It's kind of like a back door that allows me to do this very specific thing. But everything else can remain just as expressions. And so that's the kind of idea. So don't be afraid to do these things when you actually need to do your job or your work, because you have to, don't try to, I guess what I'm trying to say is, don't hardline yourself in one way. F# is a toolbox. Use the tools where it makes sense, and sometimes that does take a lot of experience. And we all should be able to provide guidance so you don't have to go through all those same mistakes, like everyone else has. So that is Foom. That's what I've been working on. Hopefully, maybe in the next 5 years, I'll have something playable. But for the most part, I can just show you some rendering and show you what I've kind of been up to. There's a lot more stuff in here that I could show, absolutely. It's just that it would be a much longer talk. Something that you didn't see in here, I actually have been messing with networking, so I have like a reliable UDP layer on top of this, so you can actually have 2 of these things running and communicating with each other, where you can see a sprite move around. But Unfortunately, we weren't able to get that working because we weren't able to connect to each other's machines. But those are the kind of things I'm exploring. And where does F# fit? It's like, remember, F# is multi-paradigm. You know, don't try to think that it's one thing. It's many things, and that is okay. So that is.
So that was a bit of Foom.
Yes.
I think nobody had any questions. Everyone was impressed by what's going on. So I will have one question.
That's okay.
I've seen an earlier demo that you were doing where you could live code and replace monsters with pictures of prominent F# personas.
Yeah. So that
is
could
this coming
be
into Foom as well?
That could there's always room for improvement.
There was definitely a suggestion in the channel that Don should replace the cyber demon, and I think our Philip PM should replace the giant spider thing, right?
Yeah. So you'll be battling prominent F# leaders.
Yeah, exactly. Well,
so what would you be? Which monster would you choose?
I don't remember more monsters than the two big ones. I'll just be the like.
You'll be the Archvile.
Which one's that?
He basically goes like this and like
Oh
summons
yeah,
fire.
right. Yeah, I like that. Yeah. Sense monads. All right.
Yeah, beware,
Cool.
or he's going to light you up.
So we've plugged in Tanner. Are you ready?
I believe so.
I believe so. We'll find out soon. So what are you going to be talking about?
I'm going to be talking about a feature that's going to be previewing in CoreCLR 2.1 called hardware intrinsics. Now, if you are familiar with C++ or native code, you might be familiar with SIMD in that they are hardware level instructions that allow you to operate on data in parallel. You have one instruction and it operates on multiple pieces of data. Generally, this is things like strings or floating point operations. So you might have a vector with 4 elements, and you want to do the same operation on all 4 elements at the same time. And SIMD allows you to do that in a very performant and efficient way.
So that will make Foom even faster, right?
Yes.
Yes, actually, that's absolutely true.
Foomier. Cool.
More Foomy, yeah.
More Foomy. So, do you have some demo to show?
Yeah, so first I'm just going to explain a little bit more about the hardware instructions. This is the Intel website that shows off all of the native level intrinsics. And you'll see we have things like add 4 elements at the same time, or perform an AND on all 4 elements. And these have been iterated upon for the past 18 plus years, starting with SSE and going all the way to the latest, which is the AVX 512 instructions. And CoreCLR 4.2.1 is previewing a feature, not yet shipping, where we are basically exposing those same APIs in a managed form, and then the JIT will recognize these instructions at compile time and basically emit a single instruction. So rather than incurring the cost of a call or having to do 4 separate adds individually, you can just have one instruction that does it. And so for 2.1, we're going to have SSE, SSE2, 3, 4.1, and the AVX instruction set. But there's others like FMA, which are planned for the future but aren't currently previewing at this time. Now, in order, as a developer, I care very much that APIs are actually usable on multiple languages. So I don't want to go and see that these hardware intrinsics are only available on C#. I want them to be usable in F# too, because I like F#. It allows me to do a lot of cool things in a very functional manner. And I'd like to do that kind of stuff fast, because F# doesn't have to be a slow language, and it isn't a slow language. In some ways, you can write more efficient code depending on the exact algorithm you're working on. And hardware intrinsics let you take that code and do it even better. So as a simple example, here's a raw bitmap that you might want to clear out. If you look at the software code, you basically have to iterate on each pixel individually and clear each one out to the desired color. whereas the equivalent code in hardware intrinsics, even though it's a little bit longer, actually compiles down smaller. And you end up doing fewer operations overall because you're writing 4 elements at the same time. Or if you're on newer hardware, you might be writing 8 or even 16 elements at the same time. So just to give you a little example, here is the software implementation, which isn't quite as flashy as Will's Foom. But it is written end-to-end.
It's flashy. Don't worry.
It is written end-to-end in F#, including the interop, all of the native windowing system, etc. So here we have just a simple software rendering. Of course, it's not very flashy, but you can see even though it's software, it's rendering at about 275 frames a second. And anyone who's familiar with Blender will recognize Suzanne there in the middle. Now, just by carefully implementing hardware intrinsics in some of the hotspots of my application, I'm able to almost double the performance here. And of course, it takes a second to recompile because if-defs were the easiest way to implement this today. But as you can see, we're now doing well over 1,000 frames a second, or thereabout, which is actually almost 3 times faster. And that was just by taking a few select hotspots like that clear function and adding a few extra lines of code to improve it. And of course, like I mentioned earlier, hardware intrinsics have a lot of different uses. You can use them for searching strings, for copying memory, or operating on arrays in mass. One of the things I was talking with Will about earlier was that F# has a lot of functions that allow you to operate on things like vectors, but these are in-dimensional vectors sometimes. And the language could theoretically, and I plan on opening a proposal for it sometime later, the language could actually take advantage of hardware intrinsics when they're supported and emit better code to make everybody's programs faster. But so some of the places where I went and did this code was obviously in the bitmap drawing section, but also in the mathematics library, where you have all kinds of various things like frustums, quaternions, and matrices, where these type of operations quickly become very important. As you can see here, normalization, although the code is longer, is still significantly faster because we can compute the dot vector with a single instruction rather than a sequence of about 20. And I wish I had more, but I think that's about the end of my demo.
Sounds good. Thanks for sharing this. So where do you see the future of F# and gaming? Is it going to be fast Foom or?
So you want like a real honest opinion. So if you're building a game even today, you should not be building a game engine like what I'm doing here as a side project. But if you actually want to build a game, I mean, Unity is probably going to be the best future for F# if it's ever going to be used for gaming at all. Unity is going to be the best bet. So I hope that there could be a lot of support on that front, because that could open up a lot of doors for people wanting to get interested in F# and gaming, because Unity is very accessible to even new people. And so I see that as probably the best possible future for F# and gaming.
All right, Unity it is then. And the sort of new hardware intrinsics, what's the sort of spaces and domains where this is going to be useful aside from rendering?
Well, like I was saying earlier, things like string processing are also very important and very core to many applications. And one of the things that's going to end up happening is after 2.1, there's going to be investigations into seeing how CoreFX itself can utilize hardware intrinsics. So we're going to see if we can utilize some of the SSE 4.2 instructions to actually make things like string processing faster. And that will, of course, extend itself to every layer because everybody uses strings.
Wow. We've got some questions right there. Question for Tanner. Although I don't think this one is super serious. I've heard the .NET runtime is slow. How did you make it fast?
Well, I didn't make it fast myself. It's, of course, a lot of effort across many people here at Microsoft. And it's always a constant effort to improve. And hardware intrinsics is just one of the many ways that we're looking at doing so.
And this is one thing that I always sort of loved about F-sharp, because it gets faster without anyone doing any work. You just wait for .NET to get faster, and bam, where F-sharp runs faster. We've got a question for Will. That's so cool. Have you figured out how to read the original Doom sound files yet?
Yeah, so this is actually kind of interesting. So not yet, but the original guy who wrote the format for the music in Doom actually works at Microsoft here, a couple of buildings away. And hopefully at some point me and him will be able to have lunch and he'll help me how to parse these files. So that's the hope. The music files are much harder than the other sounds, such as like gunshots or monster noises, because those are just wave. I could parse those easily, I just haven't done those yet.
Well, then there's some work to be done. And if we can ask our team in the back to get the first two questions away, then we can read the rest of the third one. Because right now we just have, does .NET Watch work? So what do you think? Does .NET Watch work? Can we get the third question, please? If no, then we'll just have to figure out what does .NET Watch work mean.
Well, from what I know, it's not related to F# very much, but it's a tool written for the .NET CLI and SDK. And as far as I know, it does work.
Cool. Work with Visual Studio 2017 debugging. We've got the rest of the question.
That I don't know, but I can...
That's something we'll have to talk about later with the rest of the Q&A with the F-sharp team. So thank you very much for joining us and for showing us some a bit of Foom and hardware intrinsics. This was a fun session, and I think both of the demos were flashy. And we'll be coming back to you. I think we'll actually start in 5 minutes or so with a Q&A with the F-sharp team, with Philip, Will, and we'll have some surprise guests for you as well. So stay tuned. You can get coffee and come back in 5 minutes for the last session of the fsharpConf 2018. Thank you.